In a previous video, we talked about mixtures. There are many different ways we can separate mixtures, and which ones we use are going to depend on what type of mixtures they are, as well as their physical properties. For heterogeneous mixtures, you can often use techniques like sorting, magnetism, filtration, sifting, and others. But for homogeneous mixtures and solutions, you can't generally separate them using these techniques. The solute particles are just too small. In fact, for some mixtures, they are molecules or ions. And yet, it is still possible to separate solutions and other homogeneous mixtures. The three most common separation strategies for solutions are evaporation, distillation, and chromatography. Evaporation can be a very useful technique when there are one or more dissolved salts in solution. The mixture is heated until no more liquid remains. This can either be heating by the sun or by other means, or you could just let your solution sit out and have the water evaporate over time. The solid is left behind as the water evaporates. Distillation is another technique for separating solutions. It is based on differences in boiling point and intermolecular forces. Distillation can be effective for separating mixtures that are comprised of two or more pure liquids. The mixture is heated, and the most volatile component, the one with the weakest intermolecular forces, is going to vaporize at the lowest temperature. This vapor passes through a cooled tube called a condenser, where it condenses back into its liquid state. This liquid, called a distillate, can be collected in a container. Another strategy that is useful for separating solutions is chromatography. There are several different types of this. 3 of these are called paper chromatography, thin layer chromatography, and column chromatography, but these are not the only 3 types of chromatography. Here's generally how it works, though the apparatus you use may be a little different for each type of chromatography. A mixture or solution is separated by distributing its components between 2 phases. And when we talk about a phase here, we mean a substance that's uniform throughout in both chemical composition and its state. The stationary phase remains fixed in place, and what this is made of, paper, silica gel, or alumina, depends on the type of chromatography you're doing and the types of intermolecular forces you're trying to take advantage of. Sometimes the stationary phase is polar, sometimes it's nonpolar. The choice depends on the mixture you're trying to separate. The mobile phase carries the components being separated through the medium being used. In the types of chromatography we're talking about today, this is usually a liquid. There are many different solvents and different combinations of solvents, and the choice of which solvent or mixture of solvents to use depends on what you're trying to separate, as well as the intermolecular forces you are trying to take advantage of. The mobile phase travels up the stationary phase due to capillary action. Chromatography takes advantage of the different intermolecular attractions between the components of the solution and the phases, and often this involves taking advantage of polarity. The more attraction a substance has for the mobile phase, the faster it will travel up the stationary phase. The more attraction a substance has for the stationary phase, the more slowly it will travel. When we separate mixtures, the components of the mixtures typically have different affinities for the mobile and stationary phases. This means they travel up the paper or the column or the thin layer of alumina or silica at different rates, and they separate out. Let's look at paper chromatography. Paper chromatography is a common practice for separating complex mixtures of various compounds to determine what's in them. Paper chromatography is sometimes used in the pharmaceutical industry to analyze different compounds in drugs. It's also used in forensics to analyze ink and to check for forgeries, because different kinds of ink have different pigments in them and they will separate out differently. Paper chromatography can also be used in analysis of food dyes and candies, drinks, jams, and jellies to ensure that only safe dyes are included. Paper chromatography uses a strip of porous paper, like filter paper, as the stationary phase. A solvent is chosen based on the substances that are being separated. As I noted earlier, a polar substance will travel faster and farther in a polar solvent, like ethanol or isopropyl alcohol or acetone. A nonpolar substance will travel faster and farther in a nonpolar solvent like benzene or hexanes. Here's how it works. A line is drawn near one end of a strip of filter paper, maybe about a centimeter from the end. A drop or dot of the mixture you want to separate is placed on that line. The strip is placed in a container that has a shallow layer of solvent in it, and the bottom of the paper should be touching the solvent, but the line should be above the solvent. Over time, the solvent will move up the paper strip. The mixture components that are more attracted to the solvent will be carried up the strip faster than the components that are less attracted to the solvent, and the mixture will separate. The paper is taken out of the solution before the solvent has reached the top of the container. It is then dried and analyzed. When you analyze a paper chromatograph, you use something called a retention factor, abbreviated R sub F. The retention factor is the ratio of the distance that the spot moved above the line to the distance the solvent moved above the line. The retention factor is calculated like this: RF equals distance traveled by the substance divided by total distance traveled by the solvent. As long as the conditions are the same mobile phase, the same stationary phase, the RF for a given material should remain constant in different trials, even if the solvent hasn't traveled quite as far in trial 2 as it did in trial 1. Calculating the RF can therefore be useful for determining if a particular substance is present in a mixture or for comparing the compositions of different mixtures. Thin layer chromatography is a technique that is very similar to paper chromatography, although it's typically conducted on a sheet of plastic or glass or aluminum that has been coated with a thin layer of silica or alumina, both of which are extremely polar. Since the stationary phase is polar, the more polar a substance in the mixture is, the more slowly it will travel. Thin layer chromatography is often used for separating mixtures of biological compounds or organic molecules, such as amino acids and lipids and vitamins, etc. As with paper chromatography, calculating the retention factor can be useful for establishing the identity of a particular mixture component. Fluorescent thin layer chromatography plates are also sometimes used, and these are pretty cool because they glow. Column chromatography works on similar principles to thin layer and paper chromatography. However, it uses a glass tube that has been filled with or packed with a stationary phase, which is often silica or alumina. One advantage of column chromatography is it can also work on a larger scale, and it can be used to actually purify compounds that are made in a lab. A solvent, the mobile phase, is poured down through the column. Substances in the mixture will move down the column more quickly or more slowly, depending on how much they are attracted to the stationary phase and how much they're attracted to the mobile phase. In this example, we see that the yellow component is traveling faster than the blue component, and so we can infer that the yellow component is more attracted to the mobile phase and the blue component is more attracted to the stationary phase. Now, the blue component is still moving, but it's moving more slowly. To summarize, there are several ways we can separate mixtures, and how we separate them depends on the type of mixture, whether it's homogeneous or heterogeneous, and the type of physical properties we're taking advantage of. Those strategies, like sorting, filtering, magnetism, and sifting, work well for heterogeneous mixtures. Homogeneous mixtures require different strategies, the three most common being evaporation, distillation, and chromatography, which comes in several different forms.